Lesson 3.6, we're going to focus on a special type of linear equation that we typically call direct variation. You actually studied this in 8th grade math last year, and it was usually called then proportional or non-proportional relationships, or a proportional equation. And really it's the same concept, just the vocabulary that we use is a little bit more advanced in the high school level classes. So again, it's still a linear equation. It's still sort of a subgroup or, a subgroup of the y equals mx plus b linear equation. And so let's define it first, and then we'll talk about what makes this particular set of lines special. So direct variation is when two quantities, x and y, show a direct variation and that looks like this. It's y equals and then just a coefficient and the x term, and that is it. And of course a is not 0, because if a is 0 then all of that disappears. So it's just y equals ax. A lot of times we use the letter a or k. It's still just a coefficient. It's a variable that is our unknown, and in fact when we compare this to y equals mx plus b, this is still going to represent the m, or the slope, that is attached to x. So that number a is called a constant of variation. Constant of variation. Let's fix that. Variation. There we go. And y is said to vary directly with x. Again, when you talked about this last year, you probably called it a constant of proportionality, and it was just that multiplier that was being multiplied by x to get your output. Okay, so last year you would have heard, oh, that's the constant of proportionality, and y varies proportionally to x, and we're really talking about the exact same concept, just different language that they happen to use, in algebra. So the equation y equals 2x right here, this is an example of direct variation. And in this case, the constant of variation would be, again, that coefficient that is directly connected to the x. So in this case, the constant of variation would be the 2. Okay. So this is really what I want y'all to pay close attention. So let's mark this with our little, little light bulb, a little exclamation, a little star. This guy right here. Notice that a direct variation equation, y equals ax, is still a linear equation in slope-intercept form. Okay, so it still has that format where the y is isolated, equals, and then you have an x term. So what really is the difference between just a traditional y equals mx plus b linear and this special subgroup? Well, the big difference is that the b is 0, right? That there is no plus or minus y-intercept because b is 0. So this is at the heart. And for whatever reason, honestly, I can't say that I have the answer to why they decide to use a different variable, but we just need to be comfortable with that and expect it and know that that constant of variation is your slope. So these guys are exactly the same or interchangeable. And then what really sets these guys apart is this right here, that b, which is our y-intercept, is at 0. Okay, so if you compare, all lines can be written like this. So write this down. So all lines can be written in some version of that. And direct variation is simply that same concept when b is 0, when it's absent. So it seems like a very small distinction. Oh, well, b is 0. What really is the big deal about that? Well, there's actually, you start to see that just that very subtle difference of b being 0 actually creates a domino effect, of all of these characteristics that we're going to describe in today's lesson. So the graph of direct variation equations will always have a slope of a, so that's big right here, slope of a, And since b is 0, what that means to us is that our line will always intersect the y-axis at 0, which is at the origin. So one of the defining characteristics of a direct variation is that it always passes through the origin. Okay, so if you see a straight line that passes through the origin, very immediately you should be able to recognize that as a direct variation. All right, so that's what we're going to now talk about, is being able to describe or determine if something is direct variation from equations, from graphs, from tables. So that's where we're headed today, is how to tell when a line happens to be part of this sort of special VIP group, if you will. So determine whether x and y show direct variation, and if so, identify the constant of variation. So we first need to decide, is it direct variation, yes or no? And if it is, we need to identify the constant. So the way that we're going to do this, make a little note here, is in order to be able, it's really easy to tell if it's direct variation when it looks like this. So our goal is, if it isn't already, solve for y. So we're going to write solve for the y variable, okay? And ask yourself, once it's solved, is it in that y equals ax format, okay? And if it is, great, then it's direct variation, and then we'll be able to identify the constant right in there. Okay, so that's going to be our plan of action here. Let's try it with number 1. So number 1, if needed, we're going to solve for y. So I'll look here, I'll realize, oh, but they already did that for me. That's awesome. And so the question is, if that y is isolated, does this equation have that form where it's y equals some number multiplied by x? And so by comparing that to the direct variation sort of template here, we see, yeah, that actually looks exactly like that. And so the answer, first of all, is yes, this is direct variation. And then part 2 of that is, if so, identify the constant. So then we should be able to identify that constant because it should be that number that is the coefficient on x that's directly attached there. So there is our constant of variation. So then we can say, yes, a is equal to 1/5. Just like that. Okay. Now number 2 is not solve for y. So that is what we want to do here. We want to get that y by itself. Now, since this is a 0, I actually can do that pretty nicely here by actually moving the y instead. And that way, since there's nothing here but a 0 when I move it, it's actually going to be by itself. So I'm going to end up with 3x is equal to, and over here it's just going to be a y. And maybe I'll rotate that so it's a little bit easier to compare to the y equals ax. But after rotating it around, I can see now, yep, it does have that format. So the answer here, once again, is yes, this is direct variation. And once again, the constant of variation is going to be that coefficient that is attached to the x value. Okay. So in this case, yes, it's direct variation, and the constant of variation would be 3. That's for number 2. Okay. Let's try one more. Let's say that we have, let's try this one here, number 3. Solve it for y. In this case, y is not isolated yet, so we want to get that y by itself. So let's practice that. It's been probably a few weeks since we've done this. I want to get rid of everything around the y, and I'll always start by the term that is added or subtracted, that is not directly connected. So I'll start by moving the 6x, canceling it here, and getting it on the other side with the opposite sign. This should be review. We'll cancel that. That leaves us with 4y is equal. These are not like terms, so we leave them next to each other. That's fine. And then we still have to get rid of the 4, so we'll divide everything by 4. Make sure you divide every term. And that rewrites as y equals negative 6 over 4, which reduces to negative 3 over 2. And then this right here gives us a 1/4. And now we can decide, okay, is this in that y equals mx plus b? I'm sorry, into that y equals ax. So if I do y equals ax, do these guys have the same format? In this case, the answer is no, because of this guy right here. So remember, the y-intercept has to be 0, and this linear equation has a y-intercept of 1/4, so this is a no. It's a line, it's a straight line, it's great, but it's not part of this direct variation subgroup, okay? So this one's no. So let's see, try this next one, and then you can decide if you think that that is a direct variation. Okay, so if you've tried it, first of all, we want to get y alone. So having a negative in front of this is like having a -1. And so to get rid of that, we'll divide everything by a -1 all the way across. That way the negative goes away. So we'll get y equals 15 divided by a -1 is a -15. Negative here divided by a negative becomes a positive 2x. And maybe I'll reorganize this so it has more of a traditional linear equation. And I don't know where that one came from, sorry. Just got ahead of myself there. So let's erase that. There we go, that's much better. And then we can compare this and say, okay, definitely a linear. It definitely has that y equals some x plus b, but does it have that y equals ax where there's nothing after it? The answer is no, right? So because of that -15, we can say, no, this is a linear equation, but it's not a direct variation. Okay. Try number 5. Okay, number 5, to get y alone, we will divide by 3 on both sides. That cancels. We'll be left with 2x over 3 is equal to y. And if we rotate that to make it a little bit easier to kind of spot, we've got that 2x over 3 on this side as well. Does this have that y equals ax format, or we have a y equals the x term and nothing else? In this case, the answer is absolutely yes, right? So this is a direct variation, and the constant of variation is going to be this coefficient, which is that 2 divided by the 3. I'm just going to leave that as a fraction. We know that's always a good idea. So there's the 2/3. So that's what you do to determine if an equation is direct variation. Isolate it for y and ask yourself, do you get just a y equals and then an x term? It can have a coefficient. That'll be your constant of variation, but it can only be an x term. It shouldn't have anything added or subtracted, a different y-intercept that is anything other than 0. Okay. Let's talk about being able to identify if something is a direct variation from a graph. So the big idea here is that it passes through the origin. From a graph is probably one of the easiest ways to determine is from a graph, because we check to see, does it pass through the origin? Actually, probably should be more precise. Is it a line and does it pass through the origin, right? Is it a straight line and does it pass through the origin? So it's very easy to look at, right? As long as you know that the origin is this point here where 0, 0, where the x and y axis intersect. If you see that your line passes through that origin, like on number 7, we can say, yes, this is a direct variation. However, we then have to take it a step further to find our constant of variation. So I want to remind you that our constant of variation is the same as our slope, right? We've talked about that. Oops, sorry, wrong page. It's my old answer. That's constant of variation is the slope of the line, right? The slope of A. And so as long as I can determine what the slope of this line is, what is the rise to run, then I'm okay. Now be careful here. I can go up one box and over, up and over, but really I have to be sure that I'm understanding how much each of those is worth. So even if I go up one little square, I need to pay attention to my scale here and realize that, oh, going up one square really means going up $10. So I'm going up $10 for 1 hour worked and another $10 for another, and so forth. So it's a rise of 10 to a run of 1, or in other words, just 10. That is our constant of variation, okay? In this case, it is 10. So this is our answer. Yes, it's direct variation, and the constant of variation is 10. On number 8, I look to see where is my y-intercept, and does it pass through the origin? In this case, it's all the way up here. My origin is down there. This is definitely linear, but it's not passing through the origin, so this is a pretty easy answer here. No, this is not direct variation. It does not pass through the origin, okay? And then let's write that down to be sure we know why when we go back to study. origin. There we go. Okay. And this one's yes because it passes through the origin. Okay. What about from a table of points? So we're going to do a couple of things here. It says plot the ordered pairs and use the graph to determine whether x and y show direct variation. Now, I'm going to show you that with graphing, and that's fine, but I'm also going to show you an alternative way to find out using just the table without needing to graph your points. So we're going to do it both ways. Okay. So first of all, they've given us our ordered pairs. It looks like I have positive x's, positive y's. So I probably only need a one quadrant graph here. As long as I can see where it intercepts the x-axis, that's the biggie. I mean the y-axis. So I'm going to start here. I'm going to plot these points here. And so it looks like I have a point at 1, 5. So over 1 and 1, 2, 3, 4, 5. So there's 1 point. 2, 7. So it goes over 2 and up 2 more to 7. And then 3 and up to 9. That's over here. And then 4 would go up to 11, which is a little bit off the page, but that is okay. So those are the 4 points that they gave us there if we're going by ones on our graphs. This right here is 5, 7, and then 9, and then 11 up there. 3, 1, 1, 2, 3, 4, 5. Okay, so there's our point. So the question is, if we were to connect these so we can use a pattern to get some information about where this actually intercepts the y-axis, we'll see very quickly that this graph does not intercept at the origin. And so this is a no. Okay. Now let's compare that to number 10. So if we go ahead and graph this, this one looks like I have positive and negatives on both, so I'm going to do a center 4-quadrant graph. I might even decide to go by something other than ones, but we'll go cross that bridge in just a moment. Okay, so there's our graph. And if we start to plot, I think I'm going to go by 2's on the y-axis. So this is going to be 2, 4, 6, 8, 10. That's still going to make one of those fall off, but it is okay. We're going to have enough points to know what we need to know. And then in this one, I'm going to keep it by ones. -1, -2, -3, -4, -5. Okay, so let's go ahead and plot our points. So if we've got the point 1, 5, that's going to be right here. There's 1 point. The point 3, 5, 15 is going to go up here, and it's going to be a little bit further. So that'd be 12, 14, maybe somewhere around there. -1, -5 is going to come down this way. And then -3, -15, once again, will be kind of probably somewhere over here. And if I go ahead and connect, especially the two that I actually have ordered pairs for, I'm going to graph those guys, the ones that were right there. My estimates weren't too far off. Maybe that one was a little far off. But there's our line. And the question is, does it pass through the origin? And yes, the answer is yes, it does. So, yes. Okay, it passes through the origin. However, now that we know that from a graph, it's always whether or not it passes through the origin, I'm going to give you another tool to determine this so that you don't always have to do this graphing. And it's basically you can do it any time off of a table. So one of the things that is true about direct variation that I think is pretty neat is, let's go back to the original relationship. The original relationship is y equals just ax. And for just a moment, I want you to consider, what if we reorganize this? We've done this before. Instead of having the y isolated, how would I get a by itself? If I wanted to get a by itself, I would want to divide both sides by x. And that way I could rewrite this like this. This right here is one of the main reasons why direct variation is such a big deal and it's so significant. Okay, remember, a is a constant, meaning it's like a whole number that doesn't change. Like, for example, here it was always 10. You know, it's always 10. On the example on the first page, it was 2 when we had the very first page. It was, if we have y equals 2x, then our constant of variation was 2. Literally, the word constant means it stays the same. It doesn't change. So it's not a variable. It's a constant that's going to be the same number for all of your points on your line, okay? So this is super powerful because it's one of the really big characteristics about direct variation that are not true for other lines. And that is that the y to x ratio, right, the division or the ratio of y to x will always be constant or the same if it's direct variation. So, for example, if we test that here, I didn't necessarily have to do all this graphing if I wanted to use this test instead. I would ask myself, okay, if I just put y over x here, which in this case is 5 over 1, do I get the exact same answer as if I do this y over x, which is 7 over 2, okay? Or if I do this one, which is y over x would be 9 over 3. Are these all equivalent to each other? The answer is no, and that's why this is no, okay? If that y to x ratio is not the same for all of your numbers, if 5 over 1, which is 5, is not the same as 9 over 3, which is 3, they're not equal, then we didn't even have to have graphed this to decide, oh, that line is not a direct variation, okay? But look at this one, right? This one passed through the origin. Let's look at the data points here. If I do the same test, I would end up doing negative 15 over negative 3, which we know reduces to just 5, okay? And then if I compare that to this set, y over x, that'd be negative 5 over negative 1. Guess what? That's also 5. And if we tested this one, that y over x would be positive 5 over positive 1. That's also equal to 5. So this is equal to that and is equal to that. And this last one, which was 15 over 3, guess what? That's also equal to 5. All of these equal 5. Every y to x ratio. So that's one of the really neat things about direct variation, y'all, is that it's not, you don't have to do the y2 over y1, I mean the y2 minus y1 over the x2 minus x1. You can do that for all linears, but this special group, you can literally, that's why it's called direct variation. You can directly just divide the y and the x and find out what your constant of variation is, which is your a, and also your slope. So in fact, by doing that division and getting that yes, I could even go further and actually write this equation. It's just y equals ax, because a is that 5 that we kept getting constantly the whole time. So that you can do it by graphing always and check to see if it passes through the origin, but now you know you have another tool. So let's finish these out with that in mind. Let's test it out with this method. So here, if this is direct variation, then the y to x ratio should be the same. So if I do y to x here, that's 4 over 3. So the question, of course, is 4 over 3 the same thing as 8 over 6? Does that reduce to the same thing? Well, actually, yes. If I divide those by 2, I get 4/3 again. So that one works. What about this one? It would be 12 over 9. Does that reduce to 4/3? The answer is yes. I can divide both of those by 3. And get 4/3 again. So if all of these simplify down to the exact same thing every time, this one does 2, I can divide this by 4, and I'll get 4 over 3. So all of these are equivalent to each other when I did the y over the x, okay? They were all equal for every one of those points. Then the answer here is yes, this is direct variation. I didn't necessarily have to graph it, and I can even go further and say not only is it direct variation, but that y over x, that's your a, right? So that ratio that kept coming up every time after I simplified, which all of these guys simplified to 4/3, that is my constant of variation, and then I could even just knock it out of the park here and write the whole equation for that linear equation that's a direct variation. So this is a yes, a is this, and that's your equation. So pretty neat, okay? You don't have to graph it. Let's try this last one. If we do, in fact, you try it. You try this one. I'll give you a moment, and then you can decide if that is or is not a direct variation. And so on this one, the answer is no, it is not. If you compare 4 to 2, okay, when we do that y over x, right? The first one is 4 to 2, which reduces to 2. And then when I do the very next one, that is 7 over 4, that does not equal 2, okay? That does not equal 2. It doesn't equal the same as this one. And so I don't have to test the rest. It already failed the direct variation relationship. So I can just say, oh, that's not a direct variation. It might still be a wonderful straight line, just like this one was. It could be linear, but it's just not direct variation. Okay? All right. So now that you know this really cool relationship, I kind of already alluded to it a little bit here. Let's talk about writing direct variation equations. So if we talked about this for just, a moment ago, solve the constant a in the direct variation. So let's do that one more time. If we take the traditional version and we solve it for a by dividing by x on both sides, we sort of discover this really neat characteristic that really makes these guys stand out. So the direct variation equation, y equals ax, can be rewritten like this, as long as x is not 0, because remember, we can't divide by a 0, so it can be in the denominator. But it can be rewritten like this, and therefore, in direct variation, the ratio of y to x, that's this right here, the ratio is comparison by division, is always the same for all of your non-zero data pairs. So every data pair has the same y to x ratio. And that is mind-blowing when it comes to problems like 13 through 18. The ordered pair is a solution of a direct variation equation. So we're not trying to determine if it is or not. We've been told this point is on a direct variation equation. And we want to just identify the constant and write the equation. So we want to be able to find the constant of variation, which is the a value, and write the equation all from a single point. Yeah, and it's that easy because it all boils down to this, right? As long as I have just an ordered pair, that is enough when it comes to direct variation because it gives me an xy pair. And if I already know that this is in direct variation, all I need is 1 point. All I need is 1 point to then say, well, then a is just going to be the ratio of that y value to that x value. Reduce it if necessary. And that's it. So a here in this case is 1/3. That is our constant of variation. And the equation would just be y equals that 1/3 x. There it is. Just found out everything I needed or ever wanted to know, all from one single point. How cool is that, right? So let's try number 15 here. If we use the same logic, since we already know this is direct variation, we know that the ratio of y over x will always reveal a. And in this case, y is -12 and x is -3. And then you reduce that if possible. That does reduce to a +4, right? And so we can now conclude, okay, perfect. Then the constant of variation for the equation that passes through that point is 4. The full equation is just y equals 4x. Okay, try number 17. And if you feel good about that, then we'll wrap it up here. Let's try number 17. Okay, so on number 17, again, if you compared the y over x ratio, you should have gotten -8/6. That simplified to -4/3. So that is your a value. A is -4/3, and therefore our equation was y equals -4/3 x. So if that's what you got, then you are in good shape for this. Okay, we're going to finish out these two in class tomorrow.